We continue with the discussion of flow past a rigid sphere, and you will recall that we were at d of 4 psi equal to 0. And for the velocity components, if we try to write them in spherical polar coordinates, r, theta and phi, then for the terms ur and u theta, we get the components value as this as per our substitution that we had adopted. So the boundary condition for the 4 order equation 63, which was d4 psi equal to 0, then are these: that ur and u theta, the velocity components in the radial direction and the velocity component in the theta direction, are 0 at the surface of the sphere. A is the radius of the sphere, and the velocity component in the radial direction and theta direction at r equal to infinity, far away from the origin of a sphere, will be given by as this u cos theta and minus u sin theta. A is the radius of the sphere. Then from these boundary conditions, as well as the equation, 4th order equation, solving that, we obtain that psi is equal to half ur square sine square theta as r tends to infinity. And since if the solution of psi is given in the form a function of r times the function of theta, then we can assume it to be of the form sine square theta into f of r theta. When we will substitute it in d4 psi in this form by using this equation, then the arbitrary constants that occur in the solution will take care of themselves when we apply the boundary condition. We can write the equation 63 then in the form this, and since you can see that sine theta is multiplying it, the equations can be separated in the form this. The r dependent term will be this much, and the theta term, we will have another term for which we come to later. And from these two equations that are these two fractions that are multiplying, if we take it, we can see that this is a 4th order partial differential equation whose solution can be written in general as a over r plus br plus cr square plus dr square, and when we substitute plus dr cube, and where a, b, c, of course, arbitrary constants that are to be determined by applying the boundary conditions. When we do that, we see that ur is equal to this quantity, and u of theta, the component of the velocity component in the theta direction, is this quantity. And from this we have a, b, c, d to be this equation. And consequently, the value of psi turns out to be this, and this is the solution of equation number 63, which was del 4 psi is equal to 0, and the velocity components turn out to be this. Arbitrary constants values have been substituted, and this is what we obtain.